All right, now I want to talk about the idea of continuity. Continuity has to do with where a function is continuous. Now, in order to define continuity, we're going to talk about continuity graphically. In other words, when we look at a graph, can we decide whether or not the function is continuous? So continuity, kind of the easiest way to define continuity, the way we're going to use right now, is a function is continuous if you can draw the function without having to lift your pen or your marker from the paper. Okay, that seems kind of silly, but it's actually a definition that works really, really well, and it's pretty much the definition you use until you get up into like calculus and start talking about limits. Okay, so I'm going to sketch a function, and we're going to talk about the continuity of that function. Okay, oops, x and y. All right, so let me sketch up a little function here. Okay, so here's a little function, okay? And this function has some breaks in it. In other words, we would say this function is not continuous everywhere. It has some points of discontinuity. Now, the funny thing about continuity is often when we're talking about continuity, it's easy to identify where a function is not continuous. So let's see if we can't answer this question. Where is this function discontinuous? So discontinuous just means not continuous. And in order to answer that, let's use that kind of pen on paper definition. So here I can draw this piece of my function without lifting my pen. So I'm continuous over here, but then I have a jump right here. And so I would have to lift my pen right here. So this would be a point of discontinuity. And then over here I have another point of discontinuity. So here are the two places where my function fails to be continuous, or where my function is discontinuous. And how do I identify those? Well, we almost exclusively are going to identify those by their x-coordinate. So this is x-coordinate 1, 2, -3. And this is x-coordinate 1, 2, 3. So we would say this function has points of discontinuity, or is discontinuous at x equals -3 and x equals 3. Notice I'm only using the x kind of identifier. I'm not worried about where these are discontinuous in terms of y, just x, okay? So now, if our function is discontinuous at -3 and 3, it's continuous everywhere else. So everywhere else, I could draw this function without lifting my pen from the paper. The only places I'd have to lift my pen from the paper are at -3 and 3. So our function is continuous everywhere else, or we say continuous elsewhere. And oftentimes we want to write the intervals of continuity. Okay, so we want to write the intervals of continuity. Okay, so how do I talk about where this function is continuous? Well, I'm going to talk about each kind of piece that I could draw without lifting my pen from my paper. Okay, so I've got one piece here, one piece here, and one piece here. I'm going to write an interval for each one. Now, when we are doing this, we're going to focus exclusively on x values. So I'm going to write the interval, or the domain, of this piece of my function. Well, this piece of my function starts over here at -infinity. This arrow says it continues forever, and goes until -3. So my domain of this piece would be -infinity to -3. I never include -infinity. Now this piece, right, has an open circle here. So that would be an open here, because -3 is not included on this piece of my function. I'm only looking at this piece here. Now my next interval will be this guy here. Now the domain of this guy here, he goes from -3 to +3. So this interval would be -3 to +3. Now remember, we're just dealing with this piece of my function. Here I have a solid circle, so -3 is included. Here I have an open circle, 3 is not included. So this interval goes with this piece, this interval goes with this piece, Last, we need to write the interval for this third piece of our function. This third piece of our function starts at 3 and goes to infinity. So it starts at 3, oops, gave away that, didn't I? Starts at 3 and goes to infinity. We never include infinity, and here, remember, we're just looking at this piece of my function. This open circle means we're going to have a parentheses there. So here are here are our intervals of continuity. So I could write them all down here, negative infinity to negative 3, negative 3 to 3, and 3 to infinity. And then in general, we join those with the mathematical and, which is the union symbol. So it looks like a U, but that's the mathematical and. So these would be our intervals of continuity. All right, let's put up another graph and see if we can figure out where that graph is continuous. All right, let's talk about the continuity of this graph here. Excuse me. So remember, when we're talking about continuity, it's often easiest to first identify where this is discontinuous. Okay, and if we throw out all the places it's discontinuous, then we're going to have the continuous part left. Okay, so where is this graph discontinuous? Well, remember, kind of one way to think about continuity is to think about, I could draw this without lifting my pen from my paper. So I could draw this piece here, but right here at negative 1, we have what's called a vertical asymptote. We're going to talk a lot more about those later, but the important thing is right here at that vertical asymptote, I have to lift my pen and hop over to this other piece of my function. So that means we have a discontinuity right here. Remember, we identify discontinuities by our x value at negative 1. So our first discontinuity is at x equals negative 1. Now we have one other discontinuity in this picture. Can you spot it? Our other discontinuity is right here because we have this open circle. And remember, an open circle means not included. So the second discontinuity in our picture would be right here at 1, 2, 3, 4, x equals 4. Now I do want to talk about that guy for a minute, because if you're maybe a little bit of a smart aleck like I am, you might say, hey, wait a minute, you told me that discontinuities, I have to lift my pen from my paper. I could totally draw this just by going around in a circle and not lifting my pen from my paper. Technically, you are correct. However, remember that this open circle really represents a gap in the function right there. It represents a place where our function does not exist. Open circle means not included. So our function does not include the value x equals 4. So even though technically that pen on paper analogy sort of falls apart, go with the open circle with the spirit that it was intended in terms of it's a hole in the function. Okay, so we have two discontinuities, one at x equals negative 1 and one at x equals 4. Now that we've identified those, everywhere else our function is continuous. So let's go ahead and write our intervals of continuity. So first, we'll have this interval here. Our function is continuous from negative infinity to negative 1. Negative infinity to negative 1. We never include infinity. We're not going to include negative 1 because our function actually doesn't get to negative 1. It hops over negative 1. Okay. Our next interval of continuity is going to go from here to here. So this little piece here. That's negative 1 to 4. Oops. Trying to give it away already. Again, we're not going to include negative 1. We're not going to include 4 because it's an open circle. And last, we'll have this piece here from 4 to infinity. Never include infinity. We're not going to include 4. And then we would join those together with the mathematical union symbol. That's the mathematical term for and. So this says negative infinity to negative 1 and negative 1 to 4 and 4 to infinity. These would be the intervals of continuity of this function. Okay? So when we're thinking about continuity, it's often easiest to first identify where a function is discontinuous. Where does it have a gap, a jump, a hole, a vertical asymptote? Okay? Once we've identified our discontinuities, then we can say, okay, outside of those places, I'm going to write the intervals where my function is continuous. Okay? Now, it is possible for a function to be continuous everywhere. Right? So let's just look at a couple quick examples of that. We've looked at examples that have discontinuities, but not every function has a discontinuity. So for example, if we take just a simple linear function, say something like this, nice straight line, okay, positive slope. Well, this line, right, is continuous everywhere. There's no gaps, no jumps, no holes, no vertical asymptotes. So this is continuous everywhere. And how do we say the interval of continuity for something that's continuous everywhere? Well, we say everywhere as negative infinity to infinity. So the interval of continuity for this line would be negative infinity to infinity. Similarly, what if I draw something like a parabola on this graph? We're going to be exploring parabolas very soon in this class. But this parabola, again, is continuous everywhere. There's no gaps. So this would also have interval of continuity, negative infinity to infinity. Okay? So lots of things can be continuous everywhere. Some things are not. We now hopefully know how to recognize those.